head on this because now I'm getting like, 80 submissions of all this stuff, and I overloaded the class by like 7. And so it's been an interesting few weeks. So, anyways, it's coming. The activity stuff, the grades will get put on my math lab, and I'll put out a new one sometime this week. Okay, it will happen. Sometimes this week. No, that means by Friday. Optimistically by tomorrow. It won't be, no, it's this week. It's got to happen this week. No, it's got to be this week. All right. So I do just want to finish, I do want to finish off the example I was showing you. Well, we kind of went through the regression stuff, but there was this example. We were looking at the fuel economies of cars, right? And I wanted to point out that if you look at these cars right here, notice the range of the weights, right? The range goes from maybe what? Yeah, it goes down from like 2960 up to about 47, 24 is that the biggest one? And so you could fit this data and you could get that nice regression line. This is the way your book writes it, right? You come up with that intercept and slope for predicting the miles per gallon based on the weight. But what about if you wanted to use it to do like a 6,000 pound car? Do you think that would be a good idea or a bad idea? What do you think? Why?
Because it's above.
Yeah, notice that 6,000 is way outside the range of the data. Okay, and the problem is that this is like, we have this trend between like miles per gallon and the weight, but our data only goes from like 3,000 to maybe 5,000. And we just don't know what happens out here. And so our regression lines are great, useful predictors, but we don't want to use them outside the range of our data because the truth is I don't really know what happens out here. These are very different than 6,000 pound cars, because if you get into a 6,000 pound car, you're probably talking about a large truck, right? Things that might not even run on gasoline, they might run on diesel. Okay, so this is a concept that we call extrapolation. And extrapolation is bad. Okay. And what it is it's an attempt to make predictions outside the range of your data set. So typically we just don't want to do that. All right? So if I observed some things about the people in this classroom, and maybe I was trying to make a prediction of maybe how many hours you work based on your age or something, then all of the data that I would collect within this classroom would be people in mostly the maybe 16 to 30-year-old range, just because that's who's in this classroom. So it wouldn't make sense to take that data and make predictions about a 50-year-old or a 60-year-old, right? Okay, so that's extrapolation. The last thing we didn't hit is contingency tables. Okay, so this table actually comes out of your book. And the way a contingency table works is it's comparing two variables, and it's comparing two categorical variables. So previously we looked at, with the scatter plots, you're actually comparing two quantitative variables. But in a contingency table, you're comparing categorical. So here, they're comparing level of education. That's a categorical variable, the way they've split it up. In employment status, that's also a categorical variable. And so what it does is it splits people into groups, right? So like this person right here, they didn't finish high school, and they are employed, right? So each of these groups is at the intersection of the two categories, the column and the row. Outside here, out here, this is what we call the These are in the margins. These are like what we call marginal totals. Right, so notice here, this number right here is associated with this column. So 24,395 people didn't finish high school. 61,442 finished high school, and then so on. Okay, and these totals over here are associated with the row. So 128,744 people are employed, right? Versus unemployed versus not in the labor force. And then you notice this bottom right here. That's the total. Okay. Any question? Okay, go ahead. Yeah. So if you want to compare two categorical variables, you have to use a contingency table because you can't make a scatter plot really of categorical variables because there's no natural order to the categories. It wouldn't make a lot of sense. And plus, everybody would all be piled up at the same point. You just have 10,000 dots at the intersection of did not finish high school and employed. And the graph would be really uninteresting. So, anyways, you can fill them in. If I think there's some examples in your homework where you need to look at filling in the blanks in those tables or whatever. The key basically is that notice that these rows always have to add up to that total, and these columns always have to add up to that total, and this total needs to be the sum of these. The sums should match. So the sum of this column and the sum of this total row should all add up to the same thing. Okay. Any questions about contingency tables? No. Pretty straightforward. They gave an interesting book an interesting example in the book. Then they were talking about this gender bias lawsuit that came against UC Berkeley, and the lawsuit came after they looked at this data set. I think someone was denied admittance or something, and so they felt like there was some sort of gender bias happening at Berkeley. So they looked at the data, and for a particular year, this is what they saw. And what do you notice about the difference between, say, like men and women?
Well, first off, way more, like double the amount of men got accepted.
Okay, so twice as many men got accepted as women. What about, and then what about compared to how many women versus men applied? More men applied, right? What percent of women got denied? I think that might be my next table. Let me see if I got that one. Oh yeah, I didn't. That's a different one. Notice, look at this. Out of, or accepted basically, right? So out of 1835, what percent of women actually got accepted? There were only 557 out of 1835. So what does that come out to be?
About 30%.
So it's about, what does it round to?
3035.
Yeah, so just about 30% of women were accepted. And then if you look at men, 1,191 out of 2,590 were accepted. And what does that admittance rate look like?
About 46%. It's 0.45
So what does it look like? Does it seem like they might have a case here? Maybe?
Too far off.
If you're admitting 30%, you're only admitting 30% of women, but you're admitting 46% of men. Does that look suspicious?
It's only 16%.
Yeah, it's not too far off.
Okay, so discrimination's okay as long as it's not too much discrimination? Is that what you're saying? As long as you only discriminate a little bit, then it's okay, right? So anyways, this was what they were looking at, is they were looking at the discriminate. They were looking at discrimination and saying, it looks like Berkeley is more likely to admit men than women, okay? And so they brought a lawsuit against them. So then the college was kind of like, they were pretty shocked because they didn't feel like they had any inherent bias. And so what they did is they broke it down, and they broke it into majors. And so what they did is they looked at different programs of study. So each of these is a different program of study. All right. And if you look at, so in this program of study for men, 511 were accepted, 314 weren't. 353 were accepted, 207 weren't, and so on. Okay. If you look at those numbers, what do you notice about? I think I have one with the percentages too. What do you notice about the different program breakdowns?
Whatever program A and B is, it seems to appeal more to men than women.
Yeah, notice that in program A and B, there's hardly any women applicants. Right? There were way less female applicants to programs A and B. Yeah, whereas there were quite a lot of male applicants. That's true. That has something to do with it. What else do you notice? What kind of programs are there? Any programs that women where more women applied than men? Yeah, notice here is the number of women is greater than men. Here, this one's about equal, right? This one, women are approximately the same as men. What about this one?
More women.
This one has more women than men, and this one has slightly more. Whereas over here on this program, there's way more men than women, and there's way more men than women over there. What else do you notice about the majors? Breaking it down like that. So remember, this is number accepted and number denied.
Well, some of the majors only have accept, 40 students.
Yeah, and look.
There's only 40 students.
Look at the acceptance rate. Look at the acceptance rate of like program F. How many people did they accept versus how many did they turn down? Right? I mean, they're taking like less than 10% of their applicants here in this program. And in this program, not quite as bad, but still pretty rough. They're only taking like 25% of their applicants. And what about maybe these two programs are a little bit, see, this one's more selective, this one's more selective. Notice in all these programs, they're taking less people than they're accepting overall, right? They're more picky, basically. And then notice these two programs, what's true?
That's where all the football players go?
That's where all the football players go. So this is, I can't call out any majors because I don't want to offend anybody in the room, so I'll keep my mouth shut. But anyways, yeah, so this is, here, they're actually taking more people than they're denying. They're way less picky. And so what's probably really going on here? I can look at if you look at the actual percentage rate. Compare the percentage of acceptance rates between programs. Is there really any difference within programs of the acceptance rate between men and women overall?
No, sometimes women are higher.
Yeah, you can see here, here women were accepted at a higher rate, slightly lower, slightly higher. And in fact, here women were accepted at a much higher rate than the men in this program. But then why is their overall admissions rate showing that women are accepted less often than men?
Maybe there's more men in college or applying.
Well,
Because the women are,
apply are more difficult.
yeah, the women are applying for the more difficult programs.
Yeah, exactly. What you see is that the women, in terms of the overall distribution, the women are applying to the harder programs, the more selective programs, and the men are more likely to be applying to the less selective programs. And so what you see is that in reality, actually, if you split it by program, then there is no actual gender bias. It doesn't appear to be any gender bias. It's just that there's no women applying for whatever these two majors are, whatever they are. Don't know what it is. But whatever those are, there's also a really high acceptance rate. Yeah? Kind of makes sense? So the contingency table is in the breakdown. So this is one of those examples where you have variables that confound. We talked about confounding variables. So if the gender was confounding the major variable, and so it looked like one pattern was happening in reality. It wasn't. So anyways, just a little bit on the contingency tables. All right. So thought that was a pretty interesting application. All right. Everybody cool to move on? All right. Let's do it. Okay. So we're going to go to chapter 5. All right. So I'll start you off with an example. Here are the top 5 elected officials in Washington State. You have a governor, you have a lieutenant governor, secretary of state, a treasurer, an attorney general. And what I want to know is, suppose that you just randomly pick 2. So you're just going to, maybe you're an auditor and you want to talk to 2 people in the top 5 elected officials. I want to know, what's the probability that you're going to end up with, say, the treasurer in your sample? What do you think? 1 in 5. You think so? I don't know. Well, remember, we're picking 2 people, so the treasurer just has to be one of them. I don't care who the other person is.
Still be 1 in 5, wouldn't it?
Maybe. Why would you say 1 in 5? But that would be true if I was only picking 1 person.
Well, if you pick 2, then you kind of have a 1 in 5 chance with the first pick and a 1 in 5 chance with the second pick. 2 in 10.
Well, it depends on if you pick the treasurer first, because you have a 1 in 5 chance on the first pick. If you don't pick the treasurer on the first person, then you only have a 1 in 4 chance at that point, because there'd only be 4 people left over.
So you can't choose the same person twice.
I wouldn't think so. At least not in this scenario. If you're like an auditor, you probably don't really care to talk to the same person twice. So first off, one thing we need to think about is what are the possibilities? Let's think about the possible samples. So how could we list out all the possible samples of 2 officials? What do you think? So
Go down the line and pair them up.
yeah, we just start pairing them up. So for example, we could start with the governor and start pairing him up. So you could get the governor with the lieutenant governor, so we can make order pairs, right? You could end up with the governor and the secretary. You could end up with the governor and the treasurer. You could end up with the governor and the attorney, right? Those are all the samples the governor could be paired up with. Then you start looking at, okay, how could we pair up the lieutenant governor? Well, the lieutenant governor could be paired up with the governor, but we already took that into account, right? Yeah, so the lieutenant governor will match with, could be with the secretary. That's a unique sample. The lieutenant could be with the treasurer, and the lieutenant governor could be with the attorney general, right? And then you get down to the secretary of state. The secretary of state could be with the governor or the lieutenant, but we already took care of those, right? Governor and secretary, lieutenant and secretary, we already took care of those. So we could match the secretary maybe with the treasurer and the secretary with the attorney. And what's the only sample that we haven't gotten yet? The treasurer and the attorney. So how many possible samples are there? I think I counted 10. So there's only 10 possible samples. Now, how many of them actually include the treasurer? 1, 2, 3. Is that 4? Yeah. So it's actually 4 of them. So how likely is it? It's a 4 in 10 chance, basically, right? You'd have a 4/10 chance, or that would actually reduce to 2/5 of a chance. Yeah. Does that make sense? So when we're talking about the chances or probability or the likelihood of something happening, what we need to know is we need to know, okay, first off, how many ways can this actually happen? How many ways can you actually do what you're going to do? And then you need to figure out how many ways can I see what I want to see. What's the probability, for example, then down here, that you don't end up with the governor? How many ways can you not end up with the governor?
3 to 7, 10.
One, yeah, we got 1, 2, basically all these that aren't in the first column, right? 1, 2, 3, 4, 5, 6 ways. So there's a 6 in 10 chance you're not even going to get the governor in your chance, or otherwise a 4/5 chance. You could write these as decimals too. That's 0.4. This is 0.6. Okay. So in chapter 5, if you haven't figured it out already, we're going to be talking about probability. Okay. So the basic definition of probability. So the probability of an event occurring. Okay. It's going to be a ratio of the number of ways the event can occur divided by the number of total possibilities. Okay? So if you're doing something if you're doing some outcome, if you're doing some event and the outcome is just determined by chance, and you want to know the probability of something occurring, you say, okay, well, how many ways could this possibly happen, and how many ways can I see what I want to see? And you look at the ratio. The number of ways an event can occur divided by those total possibilities. All right? So we'll start out with some simpler examples, and then we'll make it more interesting. So let's think about a lot of casino games. They involve rolling two dice, and so this dice has 1 through 6. This dice has 1 through 6. And if you look at that, typically in most of the games they involve the sum of those two dice, right? So if you roll a 1 and a 2, then your score is a 3. You sum them up. How many possible ways can you roll 2 dice? There's 6 on the first dice, 6 on the second dice.
36 in it.
Yeah, there's actually 36 ways you can roll 2 dice. So you could make we could make like a chart here, right? Think about die 1 and die 2. I think that's how you spell die. So the first die could either be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And the second one could also be a 1 or a 2 or a 3 or a 4 or a 5 or a 6, right? And so within here, you have all these different possible outcomes, right? Yeah, like that, right? So if you score if you roll a 1 and a 1, then what's the total of those 2 dice?
2.
A 2. You roll a 1 and a 2, it's a 3. But you can also roll a 3 by doing a 2 and a 1, right? 3 there. The 4s can be rolled on this diagonal, right? 1, 3, 2, 2, 3, 1. And actually this pattern is going to keep going. They'll just repeat down the diagonal. You can look at the sum of the dice. Eights down this diagonal, 9s down this one. Hopefully this works out. 11s down this one. Finally, if you roll a 6 and a 6, you get a 12. Yeah? So outside is the result of the actual dice, and inside, these are all sums. Yeah? So there's 36 ways that you can roll a 2-sided dice. Yeah? All right. So what I want to do is consider looking at some probabilities when you roll 2 dice. All right. So I'll refer back to this chart. You may want to have it handy somewhere. There's probably a picture of it in the book too. I'm not sure. Let's say you're rolling 2 6-sided dice. What's the probability that the sum of those dice is going to be an 8, right? So you go back to your chart and you say, okay, remember the basic definition of probability is number of ways that it can happen divided by the number of possibilities. So how many ways can we roll an 8?
5.
Yep, 1, 2, 3, 4, 5 ways. How many ways can you roll the dice?
36.
Yeah, so it's going to be the number of ways to get 8 over the number of possibilities. So there's 5 ways to roll an 8. There's 36 ways to roll 2 dice, and that's your answer. What does that come out as a decimal? Somebody plug that in their calculator. 139 if you round. Yeah. So you got about a 14% chance of rolling an 8. Make sense? Yeah? Okay. So that'd be your answer. You could give a fraction or decimal answer. What's the probability that the sum of the dice is less than 8? So less than 8 means it could be what? Well, it can't be 1 but it could be 2, 3, 4, 5, 6, or 7. Can it be 8? No.
Less than 8.
Yeah. So less than means strictly less than. So we're looking for all the ways you can get all the things below that. So if you go back to your chart, how many are there?
21.
Anybody else get that? That's what I got. Yeah, it's 21, right? So you count up all the outcomes that are less than 8. I counted up 21 as well. So there's 21 ways to do it out of 36 possible. I think that reduces to maybe like divide them both by 3 7/12, which would be approximately what?
58.3.
0.583.
Oh,
Yeah. Or as a percentage, yeah, it'd be 58.3%. Yeah. I mean, we typically don't deal in percentages. I usually leave them as a proportion, but you can read it as a percentage as well. Okay. All right. Any questions about that? You guys feel pretty good about that? How to calculate probabilities? All right. I think most of us have a pretty intuitive understanding of probabilities already. But one thing to think about, okay, is what does it actually mean to be a probability? Like, for example, we just saw the probability of rolling an 8. It was what was it? 5 out of 36, right?
Right.
Okay, so my question then is this. So I just gave you the probability. If you roll 36 times, will you get an 8 exactly 5 of those times?
Not necessarily.
Not necessarily. Will it happen sometimes?
It could, yeah.
It could, but it could also not happen.
Right.
Okay.
The
So what could happen?
The probability is a better chance of the outcome being true.
The better chance that we'll
If
get.
your probability is 36 out of 36, that's a guarantee you're going to get it. It's a 1. Because your probability can only be 1 through 0.
That's true. But if the probability, but what do you mean by it's more likely to happen? You mean in 36 roll, like if the probability was like 20 out of 36, does that mean I'm more likely to see 20 out of 36 rolls, or?
You have a higher chance to roll an 8. You're not necessarily going to roll an 8.
Yeah, on the next roll.
Right. On just
But
the next roll.
okay, but is it necessarily going to happen on the next roll?
No, it just means you have a higher chance.
Well, then what's the point of the number if it doesn't actually guarantee anything?
To give you a reason, educated guess.
If you do it hundreds and hundreds of times, that's probably
Yeah, the key here is that concept, because on the surface it's almost uninformative, because it's almost like saying the probability is 5 out of 36, except for if you actually roll it 36 times, guess what? You're probably not going to see it 5 times, right? It's probably not going to actually happen that way. So then, you'd think, okay, so who cares, right? But the key is it's a long run proportion, right? And so we did that 5 out of 36 is approximately, what was it, 0.139 or something? Yeah. And so what it's saying is that this is the long run proportion. It's not guaranteed in the short run, but it's guaranteed in the long run. So the probability of an event is the proportion of times it will occur in the long run. That's what probability means. It's not really talking about what's going to happen in the immediate future. It's telling us what happens in the long run. Now, it can inform our decisions, though, because it does tell us how likely, or sort of whether it's really likely or unlikely to happen in the next shot. Okay. But over the long run, is it always going to behave? In the long run, is it always going to behave that way if we do it enough times? Yeah. In fact, it's guaranteed. It's guaranteed that in the long run, if you roll two dice, and you do it millions and trillions of times, eventually you're going to see that 8 pop up about 13.9% of the time. It's guaranteed. It just might take you a while to see that, right? Okay. So that's what a probability is. Long run proportion. Okay, some properties of probabilities. So first off, probabilities always have to be between 0 and 1, okay, as a proportion. If something has a probability of 0, what does that mean?
Not gonna happen.
Yep, if something has a probability of 0, that means it never happens. If something has a probability of 1, what does that mean?
It's always gonna happen, it's guaranteed.
It's guaranteed. Yeah. Okay. So if you're trying to solve a problem and you end up with a probability that's greater than 1, that's a good indication that something went wrong. Or a negative probability, that also means probably something went wrong. Okay? Because nothing can happen less than 0% of the time and nothing can happen more than 100% of the time. It's just not possible. All right? So these are just something to keep in mind as you're working on your homework or on exam. Okay. We're going to come up with some notations so we don't have to keep writing probability over and over and over. We're getting there. Okay. So typically, when we're talking about these probabilities, we have a couple terms we use. So the sample space. The sample space we usually denote by a capital S, okay, and it's basically the collection of all possible outcomes. We typically use capital letters to denote events, okay, and then events, typically we'll use maybe a capital A, B, C, some number. Okay, these are just a collection of outcomes that we're interested in. So an event can include more than one outcome. Right. So when we looked at the example of rolling the dice, right, the event was I wanted to see an 8, but there was actually 5 outcomes that satisfied that event, right? So the event was what you want to see. The outcomes are all the ways that it can happen. And in this case, our sample space has 36 outcomes in it because there's 36 ways to roll those dice, okay? All right, so let's see. So another common thing you'll deal with is maybe playing cards, like a deck of cards. So everybody know the makeup of a deck of cards? Yes, no, maybe, so. If you don't, you should go get a deck of cards and look through them tonight.
Teach you how to play poker.
Okay, there you go. We can play some card games. If we could just have a casino day. I'll be the house. Okay. So let's think about a deck of 52 playing cards. So in a deck of cards, you got 4 suits. What's that? Spades, clubs, diamonds, hearts. 13 cards per suit. You got what? A 2 through 10, an ace down there, and then your face cards, jack, queen, king. Okay. So we can define some events. So say A is the event that the card is a king, B is the event that the card is a heart, and C is the event that the card is a face card. Yeah? So Notice we define these events with capital letters. That's basically so we don't have to keep rewriting the card is a king, the card is a king, the card is a king. We just write A. Okay. So let's define these events A, B, and C. What would be the sample space? How many items are going to be in our sample space here? If we're drawing a card from a deck, how many items are in our sample space? 52, right? So there's what? There's the ace of hearts, there's the ace of diamonds, there's the ace of clubs, there's the ace of whatever I missed, spades, all the way up to the king of hearts, king of diamonds, king of clubs, king of spades, right? And in there, your sample space is going to have 52 outcomes. How about A? What events are in A? So A was that the card is a king. How many outcomes are in A? 4, right? You got your king of hearts, your king of diamonds, your king of clubs, and your king of spades. How about B? B was a heart. How many cards are in there? Yeah, you start with your ace of hearts, then you have your 2 of hearts, all the way up to the queen of hearts, the king of hearts. Okay, so here there's 4 outcomes. And the one below it, there was
13.
This would be 13 outcomes. Right. C was that, what was there? It was, our event C was a face card. So how many face cards are there?
16.
Yeah, so you basically got, well, it depends on what you count a face card.
I would count an ace as a face card, but if you're not counting an ace, it's 12.
I think by convention, aces are not face cards
They're not.
because they don't have faces on them.
Face.
Aces don't have faces.
Oh, yeah.
I've never seen that.
Talk to a fire pilot, they got faces.
I think Jack, Queen, and King, is what we consider face cards because they actually literally have faces on them. And then you go up through the suits, and there's Queen of Diamonds, King. Gosh, dang, why do I keep doing that? King of Diamonds. And so there's 3 face cards per suit and 4 suits. So how many are there?
12.
Yeah, 12 outcomes. All right. So even though these are single events, like I want to see a face card, there's 12 ways to make it happen. All right. So what would be the probability of each of these events? So what would be the probability of A? Well, what's that? 4 over 50. I just realized I used some notation that I haven't introduced yet, but we'll get there in a second. I'll put it back up in a second. So the probability of A, that would be 4 ways to do it out of 52, which reduces to what, 1 in 13? Which would be some decimal,
0.077.
something like that.
Yeah.
Okay. What would be the probability of B?
1 in 4.
There's 13 of them out of 52. Yep, that's going to reduce to 1 in 4, which is 0.25. And then what would be the probability of C? Well, there was 12 ways to do it out of 52. That reduces to 3 out of 13, I think, which would be approximately what? 2, 2, 3, something.
0.231.
Some stuff. Yeah. Okay. Makes sense. Basic probability, not too bad. Okay. How many ways can it happen divided by the possibilities? Also, so let me go ahead and put this notation. I don't know why I didn't put a slide there for it. So the notation we use So say you're talking about an event A. Okay, the notation we use to say the probability of A occurring is we just shorthand it and we just say P of A. So when you see that big P of something, just read it as what we're really trying to find is the probability of that event. Yeah. And the reason we're doing that is I just don't feel like writing probability of A over and over and over and over again. All right. It's going to take us forever, so we just shorthand it to probability P of A. Okay. All right. But it's pretty natural notation. You'll get used to it really fast. Okay. So some other types of events that we're going to be interested in looking at is the intersection of two events. So sometimes if you have two events going on, say A and say maybe B, we use Venn diagrams in probability sometimes to visualize events. The intersection is where they overlap, and sometimes this is also referred to as the event A and B, right? So the intersection is basically all the outcomes that are in A and B. So it has to satisfy both. It has to be both one thing and the other as well. All right? So that's one type of event we're going to be looking at. All right. We also might be looking at maybe we don't care that it satisfies both of them at the same time. Maybe all we really care about is that perhaps it satisfies one or the other. And so that's an event that we call the union. All right. So maybe you only care about outcomes that satisfy either A or B. So I don't actually care about if it does both. So if you think about a Venn diagram, okay, if this is A and this is B, well, are all these people over here okay? Right? All those people are okay because they're in A. All the people in the middle are great because they're A and B, as well as all these people out here. Right? So the union just means one or the other. And it can be both, yeah. Because if all I'm interested in, if I'm only interested in talking to, in my sample, I want people who are either online students or less than full-time students, right? I don't really care if you're an online student and less than full-time because you satisfy one of my criteria, so you're good for me. So it can satisfy both and still be okay to be in the union. All right? So sometimes only one or the other criteria is necessary. And then the last type of event we're going to look at is going to be a complement event. So the complement of A it's all the outcomes that don't satisfy A. You can think of it sort of as not A. Okay. So if you're thinking about, here's your event A, and here, all your outcomes in A, then the complement is everything else. And the notation we use, at least in this book, is an A with a superscript or an exponent kind of a C, so A complement. It's everything outside the event. All right? Cool. So you can have the intersection, meaning that two events need to happen at the same time. You can have the union, meaning one or the other, I don't care. Or you can have a complement event where you're saying, I actually want everything that doesn't satisfy this. The complement is going to become useful for us. Sometimes we're going to find out that the complement probabilities are actually easier to calculate than the probabilities themselves, and we'll see examples of that. All right. So let's look at an example here, calculating. Let's go back to the example we just used. So everything's still defined the same way. So A, B, and C, you got either a king, a heart, or a face card. What if I wanted to find B complement? What would B complement be in words? What would B complement be? Yeah, it's so B complement are all the cards except, right, hearts, right? So that would be all your what, your diamonds plus your spades plus your clubs. Yeah, right. So it's everything except for the hearts. What would the event B and C be?
All hearts and face cards.
So B and C, it needs to be a heart and a face card. So it would be the face cards that are hearts. So these are face cards which are hearts, right? So this is like this would be like the Jack of Hearts, the Queen of Hearts, and the King of Hearts, right? Okay. How about B or C? B or C. Excuse me.
All face cards, and all hearts.
Yeah, so the card must be either, right, a face card or a heart. Now that's a lot bigger set. Okay. But that's what those events would be. All right? So these are the three compound events we're going to be mostly interested in. What if you wanted to do? What if I wanted to find the probability of these happening? What's the probability of B complement?
Would be your original answer subtracted from 100%.
Yeah, it turns out we're going to be able to do that with complement events. If we had to construct it just by definition, though, how many cards are in here? So diamonds, spades, and clubs, right? There's 13 of these. There's 13 of these, and there's 13 of these, right? What does that up to be? 39.
Yeah.
So there's 39 of them out of 52, and that reduces, I think, to 3/4, which would be 0.75, right? How about the probability here of B and C? Well, how many were in there?
3.
Face cards that are also hearts. There's only 3 of them out of 52. And so what does that come out to be? 3 out of 52? I have no idea.
0.058.
So about 0.5058-ish. Some change. Okay. What about the probability of B or C? How many things are in this event?
Wouldn't it be 22?
22. How do you get 22?
Well, there's 13 in the suit, but you don't want to recount the 3 face cards in that suit, so you only have to add 9 face cards to the set.
Exactly. So you think about, first off, you look at all the hearts, right? Up to the Jack of Hearts, the Queen of Hearts, the King of Hearts, right? That gets me all the hearts, but now I got to go throw in all the other face cards to this event. So now I got to throw in the Jack of Diamonds, the Queen of Diamonds, the King of Diamonds, and the other 3 suits as well, right? And so I don't need to re-throw in my hearts face cards again, though, because they're already there, right? So there's 13 of them to begin with, plus, 9 more face cards. So it looks like there's going to be 22 cards here. And so the probability of that happening is going to be 22 out of 52, which would be, 11 out of 26, which is approximately, 0.42. Yeah. Okay. Does that make sense? Okay. So what we're going to come up with tomorrow, we'll come up with some formulas maybe to help us out with these, and then look at some examples where maybe the complement's easier to calculate, and it'll all be good. My first priority, though, is I'll get that homework out tonight so you can at least get started with practice problems. All right, and then we'll go from there. Hey, what's up?
Can I give you this?
Yeah, I'll take it now.
Like that, right?
Yeah, I'll just I'll staple it to the front.
Okay.
I just don't have a
If not, my
staple.
names are on both.
That's all.
Thank you.
Thank you.
So on the homework, there's a part where it said to get the least squares regression line of something.